Hello, this is Janet and Rabia.
Welcome to Everest Physics Academy.
Before we start, we'd like to recommend our Everest Physics books for high school,
where you can find more explanations and solve applications and problems.
In this video, we are going to solve a problem about the simple harmonic motion of a simple pendulum.
A simple pendulum is formed by a particle of mass m equal 50 gram suspended from an inextensible string of negligible mass and of length L equals 0.98 meter. The pendulum is displaced from the equilibrium position, theta equals 0, by a small angle of 0.15 radians, and then it is released from rest at t0 equal to 0. Released from rest means theta prime of 0 is equal to 0. Neglect friction and use pi squared equal 10, and use for small angles sine theta is equal to theta in radians. Number 1. Determine the differential equation that governs the variation of theta. So we can start with the expression of the mechanical energy. Me is equal to the kinetic energy of the particle plus the gravitational potential energy of the system pendulum air. The kinetic energy of the particle is equal to 1/2 I theta prime squared. I is the moment of inertia of the particle about the axis of rotation delta, and theta prime is the angular velocity of the pendulum. Z is the altitude of the particle relative to the reference level. The figure shows that the altitude Z is equal to AB, and AB is equal to OB minus OA. But OB is equal to the length of the string, which is equal to L, and OA is equal to L cosine theta. Using the right-angled triangle OAP, cosine theta is equal to the adjacent OA over the hypotenuse L. So cosine theta, or OA is equal to L cosine theta. Now replace Z by L into 1 minus cosine theta, so the expression of the mechanical energy becomes 1/2 I theta prime squared plus mgl into 1 minus cosine theta. But friction is neglected, or the sum of the works done by the non-conservative forces is equal to 0, so the mechanical energy is conserved, or the derivative of the mechanical energy with respect to time is equal to 0.
So we have the expression of the mechanical energy 1/2 I theta prime squared plus mgl into 1 minus cosine theta. Differentiate both sides of this equation with respect to time. So dme by dt is equal to 0 because me is constant. 1/2 I is constant, so it remains the same. The derivative of the variable theta prime squared with respect to time is 2 theta prime theta double prime. mgl is constant, so it stays the same. The derivative of 1 with respect to time is 0, and the derivative of cosine theta with respect to time is equal to minus theta prime sine theta. So this is going to be mgl theta prime sine theta. The 2.5 cancel out. Now, we will replace sine theta by theta because the pendulum oscillates with a small amplitude, and we will take theta prime as a common factor. Now, we have theta prime is equal to 0, and I theta double prime plus mgl theta is equal to 0. But theta prime equals 0 is rejected because the angular speed of the pendulum is not always 0. It equals 0 only at the extreme positions. So we still have I theta double prime plus mgl theta is equal to 0. Divide the equation by I. This is going to be theta double prime plus mgl theta over I is equal to 0. Replace I by ml squared. This is going to be theta double prime plus g over L theta is equal to 0. This is the second order differential equation that governs the variation of theta. Let's move to part 2. Determine the expression of the natural period T0 of the pendulum in terms of L and G. Now the obtained differential equation is of the form theta double prime plus omega 0 squared theta equal 0. Now we want to compare this equation with this equation. So by comparing the last two equations, we get omega 0 squared is equal to g over L. Take the square root of both sides. So omega 0 is equal to the square root of g over L. Now we need to find the expression of the natural period. T0 is equal to 2 pi over omega 0. Omega 0 is replaced now by the square root of g over L. This is going to be T0 is equal to 2 pi times the square root of L over g.
Focus, please. This is important.
Number 3. The pendulum performs 10 oscillations during 20 seconds. Deduce the value of the gravitational acceleration in the place of the experiment. We know that the natural period T0 is the time needed by the pendulum to perform one oscillation. So 10 oscillations needs a time of 10 T0. So we can write 10 T0 is equal to 20 seconds. So T0 equal 20 over 10 is equal to 2 seconds. Now, using the formula proved in the previous slide, T0 equal to pi the square root of L over G, then replace T0 by its value, which is equal to 2 seconds. So 2 equal to pi the square root of L over G. Squaring both sides, 4 equal 4 pi squared L over G, which is equal to 40 L over G, since pi squared is equal to 10. Now, rearrange, so G is equal to 40 L over 4. Replace L by its value, which is equal to 0.98. Therefore, the gravitational acceleration is equal to 9.8 meter per second squared. Question number 4. The particle is replaced by another one of mass m equal to m. So the mass of the new particle is double that of the first particle. Specify the value of the period. The period remains 2 seconds because the period does not depend on the mass of the particle.
Let's move to part 5. Apply the principle of conservation of mechanical energy in order to determine the values of the angular velocity theta prime when the particle reaches the equilibrium position. So we need to calculate the mechanical energy at T0 equals 0, and then we will apply the principle of conservation of mechanical energy. So the expression of ME is 1/2 I theta prime squared plus MGL into 1 minus cosine theta. At T0 equals 0, theta 0 is equal to 0.15 radians and theta prime is equal to 0. This is given in the beginning of the question. Now, replace theta prime by 0, which means that the initial kinetic energy is equal to 0, and replace theta by theta 0. This is going to be ME0 is equal to 0 plus MGL into 1 minus cosine theta 0. Replace each physical quantity by its value. The mass of the particle is equal to 50 grams divided by 1000, so it becomes 0.05 kilograms. The gravitational acceleration is already calculated. It is 9.8 meters per second squared, and the length of the cord is 0.98 meters, and theta 0 is equal to 0.15 radians, and the answer is 5.39 times 10 to the power minus 3 joules. Now, we want to calculate the values of the angular velocity theta prime at the equilibrium position. At the equilibrium position, theta is equal to 0. So we will replace theta by 0 in the above expression of the mechanical energy. So this is going to be the mechanical energy at the equilibrium position is equal to 1/2 I theta prime squared plus MGL into 1 minus cosine 0. But cosine 0 is equal to 1, which means that the gravitational potential energy is equal to 0 at the equilibrium position. So we still have the mechanical energy is equal to 1/2 I theta prime squared at the equilibrium position. Now we need to calculate the moment of inertia about the wire. I is equal to ml squared. So again, the mass of the particle is 0.05 kilograms and the length of the cord is 0.98 meters, and the answer is 0.048 kilograms meter squared. Now we are ready to apply the principle of conservation of mechanical energy. So the initial mechanical energy is equal to the mechanical energy at the equilibrium position. So the initial mechanical energy is 5.39 times 10 to the power minus 3 joules. The moment of inertia is 0.048, and the answer is theta prime is equal to plus minus 0.47 radians per second. But why does theta prime have a positive value and a negative value at the equilibrium position? This is because the pendulum oscillates in the positive sense during one half cycle of oscillation and in the negative sense during the next half cycle of oscillation.
Part 6. The time equation of the motion of the pendulum is theta equals 0.15 cosine omega 0 t in SI. Deduce the values of the angular velocity theta prime of the pendulum when the particle reaches the equilibrium position for the first and the second times. Theta prime, which is the first derivative of theta, is equal to minus 0.15 omega 0 sine omega 0 t. But omega 0 is equal to 2 pi over t0, and t0 is equal to 2 seconds proved before. So omega 0 equal to pi over 2 equal pi radians per second. Now replace omega 0 by its value, which is equal to pi radians per second. This is going to be theta prime equal minus 0.15 pi sine pi t. But since the pendulum starts from one of its extreme positions, so after a time t0 over 4, it reaches through the equilibrium position for the first time. Now replace t by t0 over 4, so theta prime of 1, which is the angular velocity when the pendulum reaches through the equilibrium position for the first time, is equal to minus 0.15 pi sine pi t0 over 4, which is equal to 2 over 4. This is going to be minus 0.15 pi sine pi over 2. But sine pi over 2 is equal to 1. Therefore, theta prime of 1 equal minus 0.47 radians per second. Now, when the particle reaches the equilibrium position for the second time, it needs a time t0 over 2 in addition to the first time. So after a time 3t0 over 4, it passes through the equilibrium position for the second time. Now substitute t by 3t0 over 4. So theta prime of 2 equal minus 0.15 pi sine pi into 3t0 over 4, which is equal to 3 times 2 over 4. Then theta prime of 2 equal minus 0.15 pi sine 3 pi over 2. But sine 3 pi over 2 is equal to minus 1. Therefore, theta prime of 2 equals 0.47 radians per second. Thank you for watching. If you like this video,
Subscribe to the channel, hit the like button and share.